Hello everyone. These are the lecture slides for chapter 1.3 where we continue talking more on functions and graphs. These are some of the topics we are going to cover on functions and graphs on this lecture. First, we are going to identify intervals on which a function increases, decreases, or is constant, that is, no change in their y values. We are going to use graphs to locate relative maxima or minima. So we are going to understand what maxima and minima means. We are going to look for symmetry of a graph. We are going to identify even or odd functions and recognize their symmetries. And then we are going to talk about what piecewise functions are. And then finally, we are going to talk about something called a function's difference quotient. Here we talk about increasing, decreasing, and constant functions. Now I'm going to read out the 3 points here and try my best to explain. But if you think that you're not getting it from this slide, don't worry. We are going to go through an example and it'll be easier to understand from the example. But let's read through the wording here. It says a function is increasing on an open interval I if f of x sub 1 is less than f of x sub 2 whenever x sub 1 is less than x sub 2 for any x sub 1 and x sub 2 in the interval. All right, let me try to explain this here before we go to example. So what this is saying is, let's say we have an open interval. All right, let's say this is x sub 1. All right, x sub 1, this is x sub 2, and then this is x sub 3, x sub 4, and so on. All right, now it's quite clear here that x sub 1, right, let me pull up the pointer, x sub 1 is less than x sub 2, is less than x sub 3, which is less than x sub 4, right? The x values to the left are smaller than the values to its right. All right. Now, what this says, and also remember that f of x is the same as y. All right. F of x is the same as y. So what this says is if x sub 1 or when x sub 1 is less than x sub 2, then the corresponding y value is also less than the corresponding value for x sub 2, the corresponding y value for x sub 2. So what that would imply is that, I'm trying to get my pen here, so bear with me. It says that, let's get some y values here. All right, so in order for a function to be increasing on an open interval, the y value for x sub 1, the y value for x sub 1 should be, if it is here, it should be less than the y value for x sub 2. The y value for x sub 3, all right, should be greater than the y value of x sub 2. All right. Okay, so now let's reread this. It says a function is increasing on an open interval I if f of x sub I, that means the y value for x sub I, is less than the y value, f of x means y, again, keep that in mind, the y value of x sub 2, so this value f of x sub 1 is less than f of x sub 2 whenever x sub 1 is less than x sub 2. And as you see that, as we move from x sub 1 to x sub 2 to x sub 3 to x sub 4, that means the values are increasing. So that means a function is increasing along the open interval between x sub 1 and x sub 4, let's say. All right, provided that x sub 3, the y value for x sub 3 is less than the y value of x sub 4. So hopefully this gives an understanding of what an increasing function is on an open interval. Now, let's read the second point. It says a function is decreasing on an open interval, I, if f of x sub 1 is greater than f of x sub 2 whenever x sub 1 is less than x sub 2 for any x sub 1 and x sub 2 in the open interval. Again, let me explain that with a diagram here. So what a decreasing interval means is, what they're saying here is, we have again our x sub 1 here, x sub 2, x sub 3. Now, a function would be decreasing if the y value of x sub 1, okay, let's again put some y, mark some y values on the y-axis, just so we can plot some points. What it's saying here is the corresponding y value for x sub 1 should be greater than the corresponding y value for x sub 2. So if the y value is for x sub 1 is somewhere here, then the y value for x sub 2 should be less than whatever the y value for x sub 1 was. All right. The y value for x sub 3 likewise should be less than whatever the y value for x sub 1 and x sub 2 were. Okay, that would make it a decreasing function on an open interval. So whenever x1 is less than x2, the corresponding y values would be the corresponding y values would be greater. So f of x sub 1 should be greater than f of x sub 2, okay, whenever x sub 1 is less than x sub 2. And the third one says a function is constant. A function is constant on an open interval I if f of x sub 1 equals f of x sub 2 for any x sub 1 and x sub 2 in the interval. So in other words, that means we have our x sub 1, x sub 2, x sub 3, sorry, x sub 2. This is x sub 3. So what it says is the corresponding y values don't change. They remain the same. So the y value for x sub 1, let's say, is 1. Then the corresponding y value for x sub 2 is also 1, doesn't change. The corresponding y value for x sub 3 is also 1. So that means this is a constant function. It does not increase, okay? It does not increase or decrease. All right? So now we'll go on to an example and hopefully it will be more clear, the concept behind this. Now let's go through this example to understand what we learned about in an increasing function, a decreasing function, and a constant function on open intervals. All right. So we have been given a graph here, and from it we have to determine where or between which intervals the function is increasing, decreasing, or whether it's constant or not. So let's look at the graph from left to right. Okay, we see that the graph on the left side drops indefinitely, correct? It keeps going indefinitely. This arrow tells us that the graph on the left-hand side drops indefinitely, whereas on the right-hand side it rises indefinitely. So as we go from left to right, as the x values move from left to right, we see that the y values keep increasing. If we go back and remember what the previous slide said about increasing functions, it said that the y value, so it said f of x sub 1 should be less than f of x sub 2 when x sub 1 is less than x sub 2. All right. So if we look at the picture here, okay, we see, of course, that the graph increases between, just a second, between here all the way up to here, correct? So it says here f of x sub 1, if x1 is less than x sub 2, all right? So minus 4, let's say minus 4 is our x sub 1, okay, and minus 3 is our x sub 2. Definitely x sub 1 minus 4 is less than minus 3, correct? Minus 4 is less than minus 3. For this to be an increasing function, the corresponding y value for x sub 1, that is f of negative 4, must be less than f of negative 3. Okay, so let me pull up my pen and see the corresponding y values here. So what is the y value for negative 4? So if I drop a line here, then and extend the graph, then it touches the graph over here. So I would say that the corresponding y value, okay, corresponding y value is negative 30 maybe. All right. So f of negative 4 is negative 30. Now let's see what the y value for negative 3 is. All right. So f of negative 3, let's again drop a line from negative 3. Okay. And see that it's probably negative 15. All right. Again, this is just a rudimentary, rough, not a properly scaled picture. So f of negative 3 is approximately negative 15. All right. But the bottom line is that negative 30 is less than negative 15. So if f of negative 4 is our x1 and if negative 3 is our x2, then the corresponding y values are less than each other, right? This was negative 30, which is less than negative 15. Therefore, it satisfies the condition for of an increasing function. All right. So it okay, satisfies the curve. So it is definitely increasing between negative 4 and negative 3. And if we keep going like this between negative 3 and negative 2, all the way up to negative 2, 1, we will see that the function is increasing between between negative infinity, all right, between negative infinity and negative 1. So these are the x values. This is the interval for the x values. Okay, the y value tells us that the y values keep increasing for x values from negative infinity to negative 1. That is this point on the x-axis. So it increases, it peaks over here, but after that, it keeps decreasing, it drops. The y values drop. So what was the criteria for a decreasing function that we studied in the previous slide? It said that f of x sub 1 should be greater than f of x sub 2 when x sub 1 is less than x sub 2. Okay, that was the criteria or criterion for a decreasing function. So if our x sub 1 is negative 1, let's say, let me just use the eraser to show this value here. So uh, if negative 1 is x sub 1, and 0 is, which is less, a 0 which is greater than x sub 1, right? So let's look at this way. Let's say x sub 1 is negative 1 and x sub 2 is 0. Negative 1 is less than 0. So we have to look at the corresponding y values and see whether the y values are increasing. All right, increasing means that the y value for x sub 1 should be higher, should be greater than the y value for 0. So we see here that for negative 1, the y value is somewhere here. Let me pull up the pen again. It's somewhere here, right? Somewhere here for negative 1. What is the y value for x sub 2? It's somewhere here, which is 0. The y value for 0 is 0, correct? And it keeps decreasing until x reaches 1. All right, it keeps decreasing as x reaches positive 1. So in this interval between negative 1 and positive 1, it is a decreasing function. It is a decreasing function, and that's why they have written it here in interval form. It's decreasing on the interval negative 1 and 1. Again, keep in mind negative 1 and positive 1 represent x values. All right, it represents x values. These are x1, x these are the two x values, x sub 1 or x sub 3, whatever it may be, however many x values you want to count in that interval. But the point is that these are x values. It's not that -1 is x and +1 is y. Okay, I just want to make that clear. These are x values, the interval of x values between which the function is decreasing. And then from 1 onwards, from x equals 1 onwards, the function increases. All right, it increases all the way up, it keeps going indefinitely. All right, so 1 comma infinity, because it can keep going and going and going as x increases. All right, and the highest point we can take x to is infinity, so that's why they have it as 1 comma infinity. On the left hand side, on the spectrum of negative values, it can go as far as negative infinity. All right, so this is how you express the intervals on which a function increases, decreases, or is constant. Again, these intervals are the intervals of x values. All right. Here we're going to talk about what relative maximum and relative minimum in a graph means. I'm going to read the wordings here, but I think this can be best explained using an example. All right, but let me go ahead and read it. It says a function value f of a is a relative maximum of f if there exists an open interval containing a such that f of a is greater than f of x for all x not equal to a in the open interval. Now, in very simple terms, what this means is that in an open interval, there is one value of x in a particular open interval whose y value is the highest, is the greatest among all the y values of the other x x values. All right, that's in a summary, that's what it means. All right, there is a particular, so let me see if I can pull up a pen and explain it. So what the relative maximum means is that, let's say there is an open interval, okay, or let's say this is x1 and this is, let's say, x, all right, x something, okay. So there, in within this interval, okay, within this interval, there is a particular x, there is a particular x value whose y value is the greatest, is the highest, is the largest than all the other y values within this interval, or that this y value is the largest, okay, is the greatest among all the y values in this interval. All right, we will go through an example and it will make more sense at that point. What is a relative minimum? Let's go through the wording here. It says a function value f sub b is a relative minimum of f if there exists an open interval containing b such that f of b is less than f of x for all x not equal to b in the open interval. Again, this is just the converse of what we studied about relative maximum. There is an open interval on the x-axis and the corresponding, there is a corresponding y value. There is a particular x value within this interval. All right. Let's say this particular x value has a y value, okay, which is the smallest value relative to any other y values corresponding to the different x values in this interval. Okay, so that's essentially what it means. But don't worry if you didn't get it. We'll go on to the next slide, which talks about an example, and it'll make more sense. Here's the example, which shows us how to locate the relative maxima or minima from the graph. All right. So it says identify the relative maxima and minima for the graph of f. So what is the relative maximum? Relative maximum is in an open interval. So here our interval is, let's say, between -2 and +2, let's say. All right. Between -2 and +2. This is our open interval between -2 and +2 in this graph. We have a highest point just within this interval. All right, don't look at anything outside x equals 2. Just look at this interval. Now, within this interval, the highest point is at x equals -1. At x equals -1, we have a point where the graph peaks. All right, it peaks and then it comes down. All right, so the point where the graph peaks is called the relative maxima. Although you see that there are points, other points on the graph where the y values are much larger than than the value here, but we are just talking about an open interval, a particular interval within this graph which extends from -2 to +2. So within that interval, okay, this is the highest point. This is the peak. So that's why it's called the relative maxima. All right, relative maxima is because we are just considering a section of the x-axis, which is called the open interval. The relative minimum is at x equals 1. That is the lowest point within this open interval. All right, so at x equals 1, we have what is called a relative minimum, the lowest point. All right, so that's what a relative maxima and relative minima imply. Now we'll talk about even and odd functions. All right. It says the function f is an even function if f of -x equals f of x for all x in the domain of f. The right side of the equation of an even function does not change if x is replaced with -x. The graph of an even function is symmetric with respect to the y-axis. So let me just give you a quick example before we go on to an example in the next slide. But let me just discuss a simple example here. Okay, so let's say we have a function f, all right, f of x equals x squared. This is a function f of x equals x squared. What the definition here says is in an even function, if you substitute x with -x, then the equation should not be unchanged, or the value, once you plug in a specific value for x, will not change. Let's use a example here. For this, let's plug in a value for x. All right, let's say x equals 2, and let's evaluate this expression. So when x equals 2, f of 2 is 2 squared, correct? 2 squared, which is 4, right? What would make it an even function is if we replace 2 by its negative. All right, if x is replaced by its negative. So if 2 is replaced by -2 and we evaluate the function, we should get a 4 for our answer. So let's see, we got -2, and -2 squared is also 4, correct? Is also 4. So what we see is when we substituted x with -x, the y value remained the same. It didn't change. All right. The right hand side value didn't change. Although we changed the value of x from 2 to -2, we replaced x with -x, the y value didn't change. In this case, or this particular case, would make it what is called an even. It makes it an even function. All right, an even function. So here the right side of the equation, the right side of the equation of an even function does not change if x is replaced with -x. The graph of an even function is symmetric with respect to the y-axis. We will work on this later on. Okay. What is an odd function? An odd function says that if we replace x, like we did here, if we replace x with -x, then we will end up with the negative of f of x for all x in the domain of f. Every term on the right side of the equation of an odd function changes its sign if x is replaced with -x. So every term on the right side should change, all right, its sign. Every term on the right side should change its sign for it to be an odd function. All right. The graph of an odd function is symmetric with respect to the origin. So let me again give you an example of an odd function, an easy one here. So let's say our function is f of x equals x cubed this time. All right. So again, I'm going to work first with f of, just a second, with f of 2. So 2 cubed would be 8, right? 2 times 2 times 2. However, if we substitute the 2, if we substitute x with -x, in this case -2, we will do -2 cube. -2 to the power of 3 is -2 times -2 times -2. It becomes a -8. All right. So it becomes negative f of x. All right. So when we evaluated this function with x, with +2, we got a y value of 8. When we changed x to -x, that means when we replace the 2 with a -2, our y value became -8. All right, it became negative f of x. It became negative f of x. Negative f of x. So that's an example of an odd function. Now, if there are more terms in our function, here there was only one term in our function. If there are more terms in the function, then every term must change its sign. Okay, every term must change its sign in order for it to be uh, determined as an odd function. Here's an example of identifying even or odd function. All right. So it says determine whether the function h of x equals x to the power 5 plus 1 is even, odd, or neither. All right. So first we are trying to determine whether it's even or not. All right. So h of x equals x to the fifth plus 1. So we substitute we evaluate this function. We have h of x equals x to the fifth plus 1. Here we are replacing the x with negative x, and we want to see if we get back x to the fifth plus 1. All right, if after replacing x with negative x, we get back the original function, that means it is, and that would make it an even function. All right, so we do this evaluation. We replace x with negative x and we evaluate this function. So now we have negative x to the fifth plus 1. So negative x to the fifth, when a negative value is raised to an odd power, it is a negative value. All right, it is a negative value. So we get negative x to the fifth plus 1. This is definitely not the same as the original function. The original function was positive x to the fifth plus 1. When we substituted negative x and reevaluated it, it was negative x to the fifth plus 1. So it is definitely not an even function. H of negative x is not h of x. All right, now we see if it is an odd function or not. So let's see. We again substitute negative x and we do the same evaluation and we get negative x to the fifth plus 1. But here we see that the sign changed for the first term, but it did not change for the second term. All right. In order for a function to be an odd function, all the terms should change its sign from the original function. So in the original function, we had x to the fifth. Okay, we got a negative x to the fifth. The sign did change here. But for the next term, it was a plus 1. We still have a plus 1, no sign change here. Therefore, h of negative x is not negative h of x. The function is not odd. So the conclusion is the function is neither odd nor even. Now we go into a different topic called a piecewise function. A piecewise function is one which uh, has more than one equation, two or more equations, and those equations are specific for different x values or a range of x values. So that's why it says it is defined by two or more equations over a specified domain. It's called piecewise because it is the function is split into multiple equations for a separate range of domains, or it could be a specific x value as well. Let's look at this example of a piecewise function here. Now we said previously that a piecewise function is split into multiple functions, okay, two or more functions based on different domain intervals. All right, so let's read this function given here. It says c of t. In this case, t corresponds to x. It is a domain variable. So c of t equals, and then we use this parenthesis here to keep all the different functions together. So c of t equals 20. It's a constant value, equals 20 when t is a value between 0 and 60 inclusive. And then it says if t is a value greater than 60, then the corresponding function is 20 plus 0.40 times t minus 60. So when we are asked to evaluate piecewise functions, we have to be careful to see in which interval the given domain value, the given x value, or in this case the t value, fits, in which interval it fits, and then accordingly choose the appropriate function for evaluation. All right, so we see here it says find C of 40. So we have to look at this value 40 and see whether it fits here in this interval or in the top interval here. So 40 is clearly a value between 0 and 60, correct? It's a value between 0 and 60, so we have to pick the corresponding function that goes with this interval of t values, and we write C of 40 equals 20. Over here, this is a constant value. There's no equation for us to plug in and evaluate. It's a constant value, so we just write 20. Next, it says find C of 80. Again, we look at the value for t, which is 80, and see whether in which interval it fits. 80 is clearly a value greater than 60, so we pick the corresponding function here, 20 plus 0.4 times t minus 60. So that's what they do here. They use this equation to do the calculation, plug in 80 for t, and here we do the evaluation and we get a value 28. So C of 80 equals 28. So that's how we evaluate a piecewise function. We do have to pay special attention to the value of, to the domain value, particular domain value that we are working with, and see in which interval it fits, and then we pick the appropriate equation to work with. Now here we learn how to graph a piecewise function. Okay, so previously we've learned how to graph a function by coming up with ordered pairs from the equation of the function, an x coordinate and a y coordinate, and then after coming up with a few ordered pairs, we plot them on the coordinate system, and we then connect the points, right? Now, for a piecewise function, because we have several functions, because a function is split into several equations, we have to come up with ordered pairs from the different different equations corresponding to the domain intervals defined in the function. Okay, so let's look at the solution. We will graph f in two parts because there are two different functions here. We have to graph f in two parts using a partial table of coordinates for each piece of the graph. So we see here we have two tables, one on the left hand side, one on the right hand side. So the first table corresponds to the top function, where it says if x is less or equal to -1, then the corresponding function has a value of 3, which is a constant function. There's no equation here. If x is greater than -1, then we use this equation where f of x equals x minus 2. All right, so in the first table here, they have chosen values for x which are less than -1. So they have chosen -1, -2, and -3. -2 and -3 are all less than -1. So the corresponding y values or f of x values are this constant value of 3. So -1 comma 3 is one ordered pair. -2 comma 3 is the second ordered pair. -3 comma 3 is the third ordered pair. So because it's a constant value, no matter what value x takes, y will always be the same constant value 3. On the in the table on the right hand side, they have chosen values starting from -1, but the other values are greater than -1. So 0, which is greater than -1, 1, which is also greater than -1, and so on, right? So they have chosen uh, values in the second table which are greater than -1, and that corresponds um, to this particular function x minus 2. So to evaluate the y values, they use x minus 2. So -1, they plug in -1 into x. So -1 minus 2 is -3. 0, 0 minus 2 is -2. 1 minus 2 is -1. So these are the corresponding y values, and they put together the ordered pairs. Now they go into graphing the ordered pairs, these ordered pairs, in the next slide. Now looking at the graph of the different ordered pairs we worked for this function in the previous slide, we see that for the values of x that we chose, which were less or equal to -1, I think we chose -1, -2, and -3, but all those x values had a corresponding y value of 3. So they've plotted, if we see there's a horizontal line, okay, going from the left to the right, or rather from -1 all the way to the left. All right, it keeps going. Therefore, we have an arrowhead to this horizontal line. So it's a horizontal line which tells us it's a constant value. No matter what the x value is, when they are less than -1, less or equal to -1, the y values will all be 3. That's why we have a horizontal line at y equals 3. As for the second part of the function, which says f of x equals x minus 2 if x is greater than -1, you see what happens is we start from -1, which was the corresponding y value was -3, and then I think when it was 1, we had a y value of -1, and so on, right? At 0, it was -2 when x was 0. The y value was -2. So these were the points we plotted, and then we connected them and extended the line. However, you see that at -1, at x equals -1, we have a hollow circle. That tells us that -1 is not included, is not a part of this function. All right, even though we chose -1 as a domain value in this equation, but -1 is not really a part of this function, of this part of the function, and therefore we've indicated that -1 with a hollow circle, whereas up here, okay, up here on the horizontal line, we have indicated -1 with a solid circle. That means -1 is included in the domain of the first part of the function. All right. So this is how this is a slanting line with a slope and everything, whereas the other one has a slope of 0. This horizontal lines have a slope of 0, correct? So this is the process of graphing a piecewise function. Here we'll talk about a special expression which is called the difference quotient of a function. All right, and this is how the expression is. In the subsequent slide, in the next slide, we will be asked to perform an evaluation using this particular expression. So the expression is f of x plus h minus f of x divided by h. Okay, so what we are doing here is we are taking the difference of two functions in the numerator. Okay, the second term here is f of x, and the first term is adding h to x. So f of x plus h, and the denominator is h. Okay, this is called the difference quotient of the function f. Now here's an example of how to evaluate and simplify a difference quotient. All right, they've done this example over 2 slides, so this is the first part of the slide, of the entire process of evaluation. All right, now I'm going to write down what the difference quotient expression is. This is what it looks like. F of x plus h minus f of x divided by h. You have to kind of remember this expression. Okay, so what we are given here is f of x. We have been given the equation that goes with f of x. That's negative 2x squared plus x plus h. So when we evaluate this expression, we can just plug in this whole minus 2x squared plus x plus h for f of x. Okay, so we know what to plug in for f of x. I'm just going to surround that in brackets. This is a complete expression, f of x, right? The question is, how do we handle f of x plus h? Okay, all you do is take your x plus h and substitute that for x in the f of x expression here. So in the f of x expression, all you do is replace your x with x plus 8. Just like if they said evaluate f of 3, what would you do? You would just substitute 3 for into wherever x is in our equation, in our expression, and you would evaluate it, correct? You have to do the same thing here, only that we have an algebraic expression which we are using to replace the x with. So what we do is we replace the x with x plus h. So in the second line here, what they've done is they've shown how they are evaluating the expression f of x plus h. They took the x plus h and replaced x with x plus h. So we have negative 2 times x plus h squared, whole squared, plus they replace this x with x plus h, and then of course the plus 5. Okay, so now they are simplifying this. Now x plus h whole squared has to be expanded. All right, so it follows the a plus b whole squared formula, if you remember that from algebra. A plus b whole squared is equal to a squared plus 2ab plus b squared, correct? You take the first term, you square it, then you take the two terms a and b and multiply that by 2. So 2 times a times b, 2ab, plus then you take the second term and square it and you get your b squared. So over here, x plus h, x is the first term, so it's x squared plus 2 times x times h, so 2xh plus h squared, okay, plus x plus h. We cannot simplify this any further or expand this any further, so plus x plus h plus 5. Now, once we get that, we, you have to distribute this -2 to everything within brackets over here, and we get -2x squared, -2 times x squared, -2x squared, -2 times plus 2xh is negative 2 times 2 is -4, -4xh. -2 times h squared is -2h squared, and you bring your plus x plus h plus 5, and then we see what we can combine. Okay, in this expression, can we combine anything? We have 1 minus 2x squared, so that we don't have anything else to combine that with. We have minus 4xh, we have minus 2h squared plus x plus h. We cannot combine anything here. This cannot be simplified any further. So we have to take this entire expression of 1, 2, 3, 4, 5, 6 terms and substitute for f of x plus h. All right, this entire thing has to be this entire expression will take the place of f of x plus h, because that's what f of x plus h is equal to. All right, so let's go to the next slide and see how we proceed. So this is the second part of the evaluation. Our expression, the difference quotient, is f of x plus h minus f of x divided by h. So f of x plus h we evaluated. We came up with a 6-term expression in the previous slide, okay, which was minus 2x squared minus 4xh minus 2h squared plus x plus h plus 5. This was, let me just use my pen here and surround it in brackets. Okay, so this entire expression was for f of x plus h, the entire expression. All right, so we write that, we replace f of x plus h with the entire expression, this expression, and then minus, and then f of x was this particular expression, minus 2x squared plus x plus h. So they've written that out here. Now they have taken everything out of the brackets. So minus times minus 2x squared becomes a plus 2x squared. Minus times x is minus x, minus times positive 5 is minus 5. All right, so the signs change over here, and now we see what we can combine, how we can simplify this. And of course, in the denominator we have h, which is the denominator in the difference quotient, correct? So now let's see what we can combine. We have minus 2x squared and plus 2x squared is 0x squared, right? So this becomes 0. What else do we have? Can we combine minus 4xh with anything? No, right? We do not have a term with xh in it. Can minus 2h squared be combined with anything? No, right? We do not have another expression with h squared. How about x? We have plus x and minus x. So that x minus x becomes a 0. So that goes away, right? This plus x and minus x becomes a 0. H cannot be combined with anything, but plus 5 and minus 5 is a 0, right? So we get rid of the minus 2x squared plus 2x squared, the plus x and the minus x, and the plus 5 and the minus 5, and we are left with minus 4xh minus 2h squared and plus h. All right, and in the denominator we have our h. Okay, so now they have factored out the numerator. All right, there was a common variable h here, h in every term. We in minus 4xh we have h, minus 2h squared we have an h, and plus h. So they factored out the h. Minus 4x minus 2h plus 1 is what we are left with, and then in the denominator we have an h. So h and h divide. All right, h and h divides, and we are left with minus 4x minus 2h plus h, with h not being equal to 0. Now it's important h cannot be a 0 because we cannot divide when an expression with 0. We cannot divide an expression or any number by 0. It makes it undetermined. Okay, so that's why they have specified that, provided h is not equal to 0.